Today we're going to be covering special relativity, and we're going to be talking about the topic of time dilation. Time dilation might seem complicated, but after a little while should seem pretty simple. To start off with, we're going to talk about two facts that relativity is based upon. Number one, the laws of physics are constant in all inertial frames of reference. The second one is that the speed of light is independent of the speed of the source. These are called the postulates of special relativity. They're the two main facts we base all of our assumptions from. To start off with, we need to construct a clock. To dilate time, we need to measure time. Clocks record regular motion, and the most consistent motion is light bouncing between two mirrors. If light remains the same speed, then the ticks will remain consistent no matter the frame of reference. So, in this example shown here, we have two mirrors, mirror 1 and mirror 2. We've got one photon of light, which is just a little particle of light, travelling at the speed c, which is the speed of light, and it's bouncing between the two mirrors, which are a distance d apart. We can measure the time difference between each bounce on the mirrors as delta t. Delta just means change in. So delta t equals d over c. Now, if I were to watch this clock move along, say if it was on a train, it would move along at velocity v, let's say. So it's moving from left to right at velocity v. Between the bounces on each mirror, the mirrors move. So between M2 and M1, the mirror M1 has moved a certain distance to the right from where the light had bounced from M2. This distance that the mirrors have travelled is dependent on the velocity of the train. It'd be a greater distance if the train goes faster. So as we continue, we need to label these two different light clocks and frames of reference. We will label the person on the train looking at the stationary light clock. We will label them observer 1. And observer 2 will be the person that's on the train platform looking at the train move past them, and they'll see this version of the light clock. Now there are two similarities between these two light clocks. One of them is the distance between the two mirrors. This won't change. And the other one is the speed of light. The speed light travels along its path will remain constant. You might start to see where I'm going here. If you don't, no need to worry. So, this is the maths. It looks complicated, but I'll simplify it down. So for observer 1, we've got the changing time between each bounce equals the distance between the mirrors and the speed that the light is going, which is a constant at c. We can rearrange this, so then we can calculate the distance between the mirrors if we know the time between each tick. For reasons that I'll explain later on, we are squaring this, so we've got the square of the distance between them equals the square of the speed of light times the time difference between the ticks. For observer 2, who's stationary on the platform, they see the light move in this diagonal path. This diagonal path is dependent on d, the distance between the mirrors, and delta x prime. The prime isn't really important. It's only important when you are comparing the two frames of reference, because all we're saying is the delta t prime in observer's 2 perspective is different to a delta t in observer 1 perspective. Using the Pythagorean theorem, a squared equals b squared plus c squared, we can calculate the length that the light has travelled in the distance between mirror 2 and mirror 1. So we get this equation here, which is d squared plus delta x prime squared equals c times delta t prime all squared. Now, what's delta x prime? As I said before, the distance travelled of the mirrors between each hit is very dependent on the speed of the train. So, delta x prime equals v times delta t prime. Delta t prime is still the time difference between the two hits. Knowing this, we can also rearrange the equation so we can calculate what d squared is. So we get this equation here. So c times delta t prime squared minus v times delta t prime squared equals d squared. As I said before, d remains constant in both frames of reference. So we get this equation down here. C delta t prime squared minus v delta t prime squared equals c delta t squared. What we've done here is we've taken the inertial frames of reference, we have combined them together, and we are currently comparing the differences in how each frame of reference experiences time. So we can rearrange this into this form down here by dividing by c squared. So delta t squared equals delta t prime squared minus v squared over c squared delta t prime squared. Here we've got v squared over c squared. This shows you that special relativity only takes place when v is incredibly large. Since c is the speed of light, for a train, v is going to be insanely small compared to this. Therefore, the equation will basically limit this part to 0, and we'll just have delta t squared equals delta t prime squared. For relativistic physics to take place, you need v to be very large. On the right here, it has been rearranged, so we've got it all a nice, neat proportionality constant. This constant of 1 over the square root of 1 minus v squared over c squared will become very important later. We'll give it its own value. Now, as a summary, we've just covered time dilation, which uses a light clock that detects bounces between a mirror and another mirror above it. And for someone stationary on a platform, that uses the inertial frame reference delta t prime, they see this light clock move slower for the person on there. Basically, if I'm stationary, I see the person on the train age at a slower rate to how I'm aging. Now, weirdly, if we were to switch the frames of reference, so I was the person on the train, looking at the person on the platform, I see them moving, they also age slower. This is also known as the twin paradox, and we'll come to how that is solved later on. Thank you for watching.